So now we will be talking about how to convert, let's see here, how to convert Haworth projections into Fischer projections and determine a molecule's configuration. So to begin, we can draw a Haworth projection. And by the way, Haworth projections are specific to rings. So if we draw a 5-membered ring, or a cyclopentane, we can show it in this way, and Haworth typically places emphasis on these bonds by drawing them in bold to indicate that they are facing you. And so I just wanted to make that distinction. But anyhow, if we add a substituent such as an alcohol group, hydrogen atom, and then over here we add a methyl substituent along with a hydrogen, we can take this information and try to figure out RNS configuration. But how do we do that? Well, one of the easiest methods is to take your head and put it into the ring. So what do I mean by that? Well, if we draw this head, and bear with me on this because you may have to use your imagination. I suppose it could be some type of alien head of some sort. But anyhow, if you are facing this direction and you are staring at this carbon, we can say now that you are going to be looking at it from the viewpoint of a Fischer projection. And there's one thing I also want to distinguish, and I want to show that this molecule has this bond to the alcohol group and this bond to the hydrogen pointed straight up and down. However, they're really drawn like this. And it's the same on this side as well. So we can show our hydrogen, and over here we can show our methyl. So for clarity, I will try to erase this so it doesn't get in the way of our future reference points. So now I can go back into drawing the Fischer projection. And with the Fischer projection, we can basically show it looking like this. And once again, our horizontal bonds are pointing toward us, while our vertical bonds are pointing away from us. So if we're staring at this carbon, we know that our alcohol group is going to be on top and our hydrogen is going to be on bottom, and they are both pointing away from us. So now if we look at the molecule from the right-hand side, or we see what it's attached to from the right-hand side, we can directly see that it has a CH2. And then we move over here to the next carbon, which has a hydrogen methyl group. And we can just draw an R for the rest of the molecule. Now, if we start looking at it going left, we can see that we have CH2, and then we have another CH2, and then we move to another carbon where we have a methyl group, hydrogen, and R, for rest of the molecule. So we can see immediately that this second carbon is going to be our first point of difference, because the second carbon is attached to carbon, carbon, and remember this R group is a carbon, hydrogen. And over here, our second carbon is attached to two hydrogens and a carbon. So this one on the right-hand side is going to have priority over the group on the left-hand side. So we can now start to assign priorities. So we have 1. So now we have 1. Over here we have 2, 3, 4. And our fourth group is fortunately pointing away from us. So we're moving in this direction, and we have an R configuration. And this applies to this carbon right here. So now if we take our alien head and move it 180 degrees and now look at this carbon instead, we can compare and contrast. So now once again we will draw another Fischer projection. Pointing away, pointing away. So now we can see that up on top, or pointing away from us if we are looking at it from this two-dimensional perspective, we have a methyl group. And on bottom we have a hydrogen. And so if we look at it going to the right, starting with this carbon, we can see that we have CH2, CH2, and then we have another carbon attached to alcohol, hydrogen, and R for the rest of the molecule. So now if we're going left and we see this carbon, once again we have CH2, and then we have a carbon attached to an alcohol, hydrogen, and R for the rest of the molecule. So our first point of difference will be on this carbon. And you can see that immediately because this second carbon, if we consider this to be our first, is going to have an oxygen, an R group, which consists of a carbon, and a hydrogen, whereas this second carbon is going to have two hydrogens and a carbon. So we are going to now make our assignments, and we can assign this as number 1, number 2, number 3, number 4. So we move in this direction. And so from that, we end up with an S configuration. So S is going to represent this carbon. So now that we have determined that, we know that our total configuration is going to consist of S and R. So now let's compare it to another molecule that also uses the Haworth projection, because we'll simply draw another ring. And so if we start off by drawing a 5-membered ring, or a cyclopentane, we can now show that we have some groups attached. So let's add a hydrogen, and I'm just going to draw it going in this direction at an angle for clarity and to show or to help verify our three-dimensional analysis. So now we're going to add an alcohol. Over here we'll have a hydrogen, and on this one we will add a methyl group. So to save time, I'm just going to simply assign these, and You can verify these if you'd like, but I want to save time because there is one other point I would like to make. So if I have RR and over here I have an SS configuration, I want to show that when we compare these two molecules, we are actually looking at diastereomers. Because remember, if we take SR and we put this mirror up and then we compare it to SS, we get a diastereomer. And remember, the enantiomer of SR would be RS. But since we have SS, we know that we are working with a diastereomer because it is not a mirror image of this molecule.